Inductive and capacitive sensors are important for all types of industrial automation applications. They are used in a bottle filler or even a soda can detector. In this video we are going to understand all the characteristics that these types of sensors have. Hello everyone, welcome to Inductive. Today we will learn about inductive and capacitive sensor. We will be divided into 10 levels, where in each level we will learn more about the sensors. Okay, let's begin. Number 1. Definition. What is an inductive sensor? The inductive sensor is an electronic device capable of detecting ferrous and non-ferrous metal objects, such as steel or aluminum. What is a capacitive sensor? The capacitive sensor is an electronic device capable of detecting metallic and non-metallic objects, also liquids and solids, such as water or plastic. Number 2. Composition. The inductive sensor is composed of detection zone. It is the area where the sensor detects the presence or absence of a ferrous or non-ferrous metal object. This zone is determined by the sensor's ability to detect changes in the magnetic field. Coil. It is the main component, since it is an inductor, which generates a magnetic field when an alternating electric current is applied. The presence of a metallic object alters this field, which changes the inductance in the coil. Oscillator. It produces a high-frequency signal that is applied to the coil to create the magnetic field. This signal is modified when a metallic object affects the magnetic field. The resulting variation is used to determine the presence or absence of the object. Rectifier. It converts the alternating signal generated by the coil into a direct current signal. This stage may include a rectifier circuit to convert the output signal into a usable format. Comparator. Compares the rectified signal with a preset threshold. When the signal exceeds this threshold, the comparator activates the output stage to indicate the presence of the metallic object. Indicator. It provides an output signal that indicates the presence of the metallic object. A light-emitting diode is placed as an indicator. Exit stage. It generates an output signal that is used to activate or deactivate a device or a control system based on the detection of the metallic object. The capacitive sensor is composed of detection zone. It is the space in which the sensor is capable of detecting the presence or proximity of an object. When an object enters this area, changes occur in the capacitive properties of the sensor, indicating its presence. Condenser plates. These plates are fundamental elements of the capacitive sensor. They consist of two conductive surfaces that act like the plates of a capacitor that generate an electrostatic field. The proximity of an object affects the electrostatic field and the capacitance between these plates. Oscillator. It produces a high-frequency signal that is applied to one of the sensor plates. The presence of an object alters the capacitance and, therefore, the oscillation frequency. This variation in frequency is monitored to detect changes. Rectifier. It converts the high-frequency signal generated by the oscillator into a direct current signal for further processing. Comparator. compares the sensor output signal with a predefined threshold. When the capacitance exceeds a certain level, the comparator activates the sensor output signal to indicate the presence of the object. Indicator. It can be a visible component or an electrical output that indicates the detection of the object. It may be a light-emitting diode. Exit stage. Provides an output signal that informs other devices about the detection of the object or the proximity of the sensor. Number 3. Operating principle. The inductive sensor has the following operation. When the metal object is far from the detection zone, its oscillation amplitude is high and constant. This means that the signal is strong and stable. Also, the indicator is off. When a metal object approaches the sensor, the inductance of the coil changes, increasing the load on the oscillator. This reduces the oscillation amplitude, meaning the signal weakens as the object gets closer. The decrease in amplitude is proportional to the proximity of the object and its size. The indicator lights up. The capacitive sensor has the following operation. When an object is far from the detection zone, its oscillation amplitude remains stable. Also, the indicator is off. When an object such as a glass of water approaches the capacitive sensor, the capacitance between the sensor plates increases. This causes an increase in the oscillation amplitude of the signal. The closer the object is, the greater the amplitude. Number 4. Sensor shield. There are two types of inductive sensors, shielded and unshielded. The unshielded sensor can be normally open or normally closed. It is also characterized by having a free detection zone since it does not have a metal ring surrounding the core to restrict the field. These are usually mounted flush with metal, and have a greater sensing distance than shielded sensors. When we bring the metal sphere closer, it detects the entire free zone of the sensor, be it top, middle, or bottom. The normally open one closes, and the normally closed one opens. The shielded sensor can be normally open or normally closed. It consists of a ferrite core inside where the field is concentrated. These are mounted at the root of a metal. Their sensing distance is limited in a straight area compared to the unshielded one. When we bring the metal sphere closer, it is detected in the entire straight area of the sensor. The normally open one closes, and the normally closed one opens. Now, capacitive sensors can be shielded and unshielded. The unshielded sensor can be normally open or normally closed. Their electrostatic field is less concentrated since they do not have a metal band around their probe, but they are capable of detecting materials with high dielectric constants, which allows comparing materials with high and low constants. They have a greater sensing distance. When we bring a glass of water close to it, it is detected in the entire sensor detection area, be it top, middle, or bottom. The normally open one closes, and the normally closed one opens. The shielded sensor can be normally open or normally closed. Their electrostatic field is more concentrated since they have a metal band around their probe. They are capable of detecting materials with low dielectric constants that are difficult to detect and have a limited straight sensing distance. When we bring a glass of water close to it, it is detected in the entire sensor detection area in a straight area. The normally open one closes, and the normally closed one opens. Number 5. Sensing materials. Most inductive sensors are governed by a general correction factor table, for various ferrous metallic materials such as steel and non-ferrous materials such as brass, aluminum and copper. Well, we begin to sense ferrous metals, which have a correction factor of 1. If the inductive sensor has a nominal sensing distance of 10 mm, and steel is a ferrous metal, the sensing distance will be 10 mm. Now the brass, which has a correction factor of 0.5. If we multiply it by the nominal distance of the sensor, it gives us 5 mm, which is the sensing distance for brass. Aluminum has a correction factor of 0.45, multiplying it gives us 4.5 mm for the aluminum sense. Now the copper is the lowest with a factor of 0.4, multiplying it gives us 4 mm, and its sensing distance from the copper will be that. Well, now the capacitive sensor. These are governed by a general table of dielectric constants, and also a graph that represents the dielectric constant of an object versus the ability of the sensor to detect the material based on the nominal sensing distance, called SR. We have 3 materials. Water, with a dielectric constant of 80, which represents 100% in the graph. If we have a capacitive sensor with a nominal sensing distance of 10 mm, the sensing distance of the water will be 10 mm. When the water is brought closer, the sensor still does not detect it. We need to calibrate its sensitivity using the potentiometer and turn on the light-emitting diode. Now the alcohol that has a dielectric constant of 25.8. According to the graph, it is equivalent to 85%, that is, when multiplying it by 10 mm, it will give us a sensing distance of 8.5 mm for alcohol. We calibrate the sensitivity and that's it. Next is the wood. With a dielectric constant of 2.7, which is equivalent to 12%, multiplying it gives us 1.2 mm of sensing distance for the wood. We calibrate the sensitivity and that's it. Number 6. Switching hysteresis. If we have a sensor, be it inductive or capacitive, with a nominal sensing distance of 10 mm, we approach an object which detects at a distance of 8 mm. And when you move away, it stops detecting within 9 mm. The hysteresis will be the area from the distance point of the switching when approaching and moving away. Hysteresis is important to avoid the effect of rebounds produced by the vibration of the object to be detected and thus not affect the operation of the sensor. Number 7. Sensor models and connection. We have the 2-wire sensor. We will connect it to a 24-volt continuous source, and to a relay, to test its operation. The sensors are usually the brown wire, positive voltage, the blue wire, negative voltage. Before connecting, never connect it directly to the power supply, because when the sensor goes to sense, it shorts out, so for that we need the relay. The first connection, the sense load will be positive, so we connect the negative, blue, to the negative of the source. In the relay, we have a coil on terminals A1 and A2. A1 is the positive side, and A2 is the negative side. We connect the positive, brown, to the negative of the relay, A2, and to close the circuit, the positive of the source, to A1, positive of the relay. We turn on the source with alternating power in L and N. Now we are going to sense. We bring the object closer to the sensor. The relay and the sensor indicator are activated. We move it away, it turns off. Now we connect the positive, brown, to the positive of the source. We connect the negative, blue, to the positive of the relay, A1, and to close the circuit, the negative of the source, to A2, negative of the relay. We are going to sense. We bring the object closer to the sensor. The relay and the sensor indicator are activated. We move it away, it turns off. Three-wire sensor, they usually have a brown cable, as positive voltage, blue cable, negative voltage, and black cable as the signal. Since internally these have a transistor that can be a PNP or NPN signal, we start as if it were an NPN signal sensor. The brown and blue cable connects to the positive and negative of the source, respectively. The black cable is connected to the negative of the relay, A2, and the positive of the source, to A1. We are going to sense. We bring the object closer to the sensor. The relay and the sensor indicator are activated. We move it away, it turns off. Now we have a PNP signal sensor. The black cable is connected to the positive of the relay, A1, and the negative of the source, to A2. We are going to sense. We bring the object closer to the sensor. The relay and the sensor indicator are activated. We move it away, it turns off. We also have the 4-wire sensor that has the following diagram, where it is similar to the 3-wire sensor, only unlike this one, it presents two signals that are normally open and normally closed. Number 8. Connections with a PLC. Whether we have a capacitive or inductive sensor, the connection is the same for both. Usually 3-wire sensors are placed to be able to sense it with a PLC. For this we have the Siemens S7-1200 PLC. We connect in the following way. The positive voltage of the sensor, brown, to the L+ of the PLC. The negative voltage, blue, to the M of the PLC. This is the internal power supply that the PLC has. If the sensor has a PNP signal, we join the M with 1M of the PLC and the sensor signal, black, to input 0. We connect the alternating voltage, L1 and N, of the PLC. We turn on the PLC, it is in run state. We are going to sense a glass of orange juice. We bring it close to the sensor. We calibrate the sensitivity. Input 0 of the PLC and the sensor indicator are activated. We move the glass away from it, and it stops sensing. Now if the sensor has an NPN signal, we join the L+ with 1M of the PLC. We are going to sense. Input 0 of the PLC and the sensor indicator are activated. We move the glass away from it, and it turns off. Number 9. Response frequency. The response rate of a sensor refers to the speed at which the sensor can detect and respond to changes in the presence or absence of a detectable object. In simple terms, it indicates how quickly the sensor can detect a change in the object's proximity and generate an output signal accordingly. We can find all this in its specifications. For these applications, inductive sensors are mostly used. Well, in this case we have a PLC that will be in charge of processing that data. We see its connections. It is a 3-wire sensor with a PNP signal. In an HMI we can display the motor speed. We start the engine. The speed begins to increase. It reached its maximum speed, 1800 RPM. Now slow down to a stop. Number 10. Sensor applications. We have a water bottle filling machine with its complete process. If you want to know how to program with the PLC, I will leave a label up here after you finish watching the video. We can see that the machine uses only capacitive sensors. First, the filling process. Detects 3 viddens, starts filling, until the sensor detects. This process is the cap screwing. It detects the capacitive sensor and activates the process. Finally, the labeling process. Next is a soda can counter machine, which uses an inductive sensor, which verifies if the cans are closed. Thank you for watching the video. Don't forget to subscribe to the channel for more videos. Leave your like. Have a good day. Bye.